Good morning everybody. Today let us discuss about RC circuit, how an RC circuit works, what is R, what is C, and what is it we are going to understand with this RC circuit. This is an experimental arrangement. So first let us discuss a little brief theory about RC circuit, and then let us go on to the instrument, record the readings, plot a graph, and calculate the time constant of RC circuit. Now what is time constant here? Time constant, the time taken to get stabilized. The constant value, the time taken to get a constant value. Now what a constant value is? Stabilization. Or in short, if I want to put it in this way, how much time it is taking for this RC circuit to get charged up, or how much time it is taking for this RC circuit to get discharged. So let us see the simple RC circuit. This is the voltage source. Here you are going to have a resistance and a capacitance and an ammeter. So here the voltage is given, R is given, C is given here. Anyway, we are going to measure in terms of micro. So here R stands for resistance. Now what is resistance? The obstruction to flow of current, in fact charge carriers. The obstruction to flow of charge carriers, we call it as resistance, and resistance is available everywhere. There is no element where you have a zero resistance. Now what is capacitance? The capacitance is a word which has been derived. What is the capacity of that element to store the energy, because capacitance is nothing but it stores the energy. But this is also another form of resistance, and what exactly it is doing? It is also acting like a resistance. This resistance is an active resistance. Capacitance has a passive resistance. In fact, we call it as inductance. So the resistance in the capacitance we call it as inductance, and the resistivity in the resistance we just call it as resistance. Now what is this resistance is going to do? It is going to abstract the energy, convert that energy into heat. So this R is going to convert energy into heat, and the same, the inductance in the capacitor, once again what it is doing? It is going to convert this into electric energy. So the resistance is going to store energy in the form of heat, and capacitance is going to store the energy in the form of electricity. So in short, what is that we are going to do? We are going to find out how much amount of energy it is going to store. Because anyway heat it is already there, we are going to find out how much amount of electric energy it is storing, or how much time it is taking for the electric energy to get stored here, or how much time it is taking for this stored electric energy to get discharged. So we have a charging as well as a discharging. So it's a very simple series circuit, voltage source with an ammeter, R and C, which are all connected in a series conditions. So the graph, the observation or when the circuit is connected, here we have AC source, but we are going to take a DC source. We are going to have AC source, we have AC and DC, but for the experimental, because of the limitations, we are going to go for a DC source. So this DC source is converted to the resistance. It abstracts a little amount of energy, converts that into heat, stores in the form of heat, and the remaining energy will be going to the capacitor. Capacitance also abstracts the energy in the form of inductance and stores in the form of electric energy, and the remaining will be measured by the microammeter. So the tabular column will be serial number and how much time, in what time, and what is the charging value. Similarly, you are going to have another table, serial number and time, and what is that you are going to have? Discharging value. So here, what is that we are going to do? We are going to connect the circuit. After connecting the circuit, we are going to take the stop clock, and with respect to time, how much time this whole combination is going to take to store the maximum energy. In short, or in a reverse way, the same circuit, we are going to take the circuit and we are going to take a stop clock, and how much time it is taking to discharge the energy. To know this, I will give you a simple example. We already have this example. Like for example, we have water motors, the water pumping motors as well as the fans. Immediately when the fans or water motors are switched off, the electricians, they never touch a capacitor. Why they don't touch a capacitor? Because immediately after switching off these fans or motors, there is a little amount of electric energy stored in the capacitor. Immediately you just go touch a capacitor, what happens? We receive a shock. So what is that they will be doing, the electricians? They will be waiting a little amount of time or spending a little amount of time so as to service these machines. So we need to find out how much time it is taking for this energy to get discharged. So the charging anyway, it's a rapid process, the time taken will be very short. So we will be just going for a discharging part, because it takes a little more amount of time where we can comfortably understand and measure the sequences. So here, what is the way we are going to take? We want to connect a circuit. and we are going to charge it up. After that, we are going to take a stop clock. We are going to switch off this power source and find out how much time it is taking for this circuit to discharge the total energy available in this equations or in this circuits. And here what is that we are going to calculate? We are going to calculate the total time taken. For this, what is that we will be taking? We will be taking I equals to I naught into exponential of minus T by RC. This is the major equation we are going to take, where I naught is the maximum amount of current that is generated when we are going to connect in the circuit, and T is the total time taken or instantaneous time. At what time we are measuring this? R, the resistance value measured in form of ohms. C, the capacitance value measured in form of farads. And this is the instantaneous current at any time period T. I naught is the maximum current, instantaneous current which is measured with respect to time. We are going to take this equation, we are going to take this discharging quality and find out how much time it is taking, or what is the theoretical value calculated from this, and how much amount of practically measured time to discharge the total energy. Right? So let us start the experiment. Okay, so this is the RC circuit we have. These are the different resistances we have. These are the different capacitances, and this is a built-in model. So here we are just going to plug in and just find out what are the characteristics we can study from this given RC circuit board. Here we have a microammeter. We have 3 different resistance values, 3 different capacitances, and the circuit is inbuilt. So here let us connect the circuit. Here what is that we have? We have a plus ammeter, and here the meter is given here. So we are going to connect the positive of this capacitor to this meter. Similarly, the negative of this ammeter is connected to the negative available here. And then here, what is that we have? We have a charging power supply here, and this power supply should be given to the input here. So the minus is given to the minus here, and the plus is plus. We are going to connect this plus to the plus. And similarly, we have different R's, different resistances and different capacitances. So finally, what is that I'm going to do? I'm going to take the positive of one capacitance, and here already we have a capacitance positive indicated here. Just connect this, and the negative of capacitance. This negative of capacitance is connected to the negative of this. Similarly, resistance. This resistance here, it is connected to the resistance here, as well as the second port of the resistance is connected to the second port here. So now the circuit is connected. And this is the stop clock we are going to take. So I'm going to reset this. So the stop clock is reset. Now first, what is that I'm going to do? I'm going to on the circuit. After this on the circuit, I'm going to charge it up. So the circuit is on, the bulb is glowing here. So the circuit is on. Now the charge is happening. The complete here, what is that we have? Here the maximum value what we are going to get is approximately 80 to 84 microammeters. So that's what I said in the beginning. It takes a very short period of time for this whole circuit to get charged up. That's the reason why we are not going to calculate the time taken for the charging. We are going to calculate only the time taken for the discharging part. So now what is that I'm going to do? At the same time, I'm going to off this, I'm going to on this. I'm going to on the stop clock. So now the stop clock is on, the reset, and fine. So for every 5 seconds, I'm going to note down what is this we are going to get. So for every, now it is 10. For 10 it is approximately 78. For 15 it is approximately 78. For 20 it is approximately 76. And for example then it is 25, it is 76. And then it is 74. Then once again you're going to have 74. Then 72. Followed by 72. And then you have 70. Once again it is 70. Just focus this here. Then followed by 68. Then it is once again 68. Then 64. This is the stop clock which is running here. 64. And once again here we got a 64. And once again we got 62. Similarly you're going to get 62. So for every 10 seconds actually it is happening, but I'm measuring for 5 seconds. Then you're going to have 60. And then you're going to have a 60. So now I'm going to go for 58. Now from here the time, it takes a little more amount of time here. So once again 58. Then what is happening? 8. So it is now 56. then it is 56, then we have 54. Similarly, we are going to have a 54, then we have 52, then we have 52, then 50. Now it is once again 50, then 48, 48, 46, 46, 44, 44, once again 44, 44, 42, 42, 40, pause, 60, 65, 70, 75, 80, 75, 180, 185, 190, 195, 200, 205. So now let us draw the graph here. Time is always measured on x-axis and the ammeter reading always on y-axis. Now the question is, why time is always on x-axis? Why can't time be on y-axis? It's very simple. Anything which is independent should be on x-axis. That's a fundamental rule. When the graph theory was generated, anything which is independent is on x-axis. Anything which is dependent on this will be on y-axis. Here time is independent. The charging period or discharging period is dependent on the time, and therefore what is that we are going to take? On y-axis we are going to take the ammeter reading here. We are going to take the ammeter reading, and here we are going to take the time period. So here I am going to divide each block into 10 seconds. So what is that I am going to get? 10 seconds, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 160, 170, 180, 190, 200, and so on. Now let us take the values on ammeter. Ammeter, it is starting from 80 to 40. And how many blocks we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So approximately 10, 10, 10. We are going to take 10, 10, 10. So let us start with 10 microamperes, 20, 30, 40, 50, 60, 70, 80. This will be a very short graph. So what is that we will do? In place of this, we will be taking 5, 5, 5. Each 5. Let us take each one as 5. So this will be 0, 5. Each block 5 units. 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80. So this is what we got. So exactly at 10 seconds on this time here, 10 seconds we have 78. So we are going to take 10 on x-axis and 78. This is 75, this is 80. So 78 somewhere will be here in this part. And then 20 we have 76. So let us go for 20, and this is 75. So this is. And then once again for 30 we have 74. So let us go for 30, 74. So somewhere here it will be. And then for 40 we have 72. So this is 40, we have 72 here. And then for 50 it is 70. So this is 50, and this is the 70 value. And then for 55 also it is 70. So 55, I mean for 60 let us take 60, it is 68, because we are taking for 10 seconds. So let us take this 60. 60, what is that we got? 68. And then for 70 it is 64. So 70 we are going to take, this is 64. And 80 it is 62. 80 we have 60 here, so this will be the 62 point. And for 90 it is 60. So 90 here and 60 is available here. So this is how it is. And then for 100 it is 58. So 100 we are going to go for 55. This is 58. And for 110 it is 58 once again. So 110 also we are going to go for the same 58. And 130 we got 54. So let us go for 130. Sorry, 120 we got 56. So this is 55, 56. This is 56. And then here for 130 it is 54. So this is 54. And then for 140 it is 52. So 140 it is 50, 50, 52. In that way, just point out the. So after plotting the graph, let us connect the points. When we connect the points, this is what we are going to get. We are going to connect the points in this way. This is how exactly. So this is the decreasing charge we are going to get. In this value, what is the maximum value we got? The I naught, the I value. I naught is value is given as 80. So let us take it as 80. We need to calculate I value. Now let us take R and C values. Let us come back to the circuit here. The R value here it is given as 57 kilo ohms. R value is given as 57. And what is the C value? The C value is also mentioned here. The C value here it is mentioned as 4700 microfarads. So it is visible here. 4700. So it is 4700. Yeah, just it is 4700 microfarads. So now let us take these values and do the calculation part. So R value is given as 57 kilo ohms and C value is given as 47,000 microfarads. So what is the value of RC? So what are we going to do? We are going to multiply 57 kilo into 47,000 micro, which is nothing but 57 into 10 power 3 into 4700 into 10 power minus 6. So finally what is that we get? 57
into 47.
57 into 4700. We get 267,900 into 10 power 3 minus 6. So this is 267,900 into 10 power minus 3. We get 267.9. So this is the value of RC. So what is that we get? I equals to I naught into exponential of minus t by RC. We are going to calculate this value. So from this, the maximum value I naught we got as approximately 80. So divide this by E value, the exponential value. So what is the exponential value? The exponential value is always given by e power minus 1 or e power 1. So this is 80 divided by 2.71. So we're going to divide this 80 divided by 2.71. So we get 29.5. So this is 29.5. This is the I value at any instant of time. When we are assuming that t equals to RC, then I becomes I naught into e power minus t by t, or I equals to I naught by e, or I value is 29.5 microamperes at any instant of time. And this is the time taken. The time taken is given by 267 seconds to completely get discharged. So this is the at any instant of time, this is the current that is available, and this is the time which is taken for discharging. So we know how to calculate, or for using these values we come to a conclusion that this amount of time is required for the discharging of the given RC value of 57 kilovolts and 47,000 microfarads. Thank you.